Hello and welcome to the lecture Autoregressive Model. In this lecture, we first define what we understand about autoregressive model. Then two autoregressive model we are going to discuss, namely pixel RNN and pixel CNN. And then we discuss different generative AI model for NLP and mission task as an examples. Today we start another different kind of generative model called autoregressive generative model. In autoregressive generative model, the element is generated a step-by-step fashion. By definition, an autoregressive generative model is a type of machine learning model that generates data step by step by predicting the next element based on the previous ones. Now that is a very important to understand. Let's consider a sentence that India is a great country. Now if we want to generate this, we not generating the entire sentence at once. Rather, it generates the word one by one. As first India, then is, then a, then great, then country, and so on. Okay? And when we predict India, it predict as its own. Then in generate is, it depends on the India. Then A depends on India is. Great, India is A. So what can see what are the previous generated words? We depend on these previous generated words for predicting or generating the next word. And that's why the meaning or the word autoregressive comes. It means model predicts the next value using its own previous outputs. These kind of models are very much useful in NLP, image generation, audio synthesis, time series forecasting, and different applications. So, what we basically understand it, instead of generating an entire sequence at once, the model generated one by one element at a time, and when generate element, it depends or it conditioned on the previously generated data or words or elements. So mathematically, if we write, then this joint probability is realized by means of P of x1 times P of x2 given x1 times P2 x3 x1 given x1 x2 given, and so on. So this model learns the conditional probability of the each step. So this is first time instance, second, third, and so on. So this is as well a basic definition or a very naive understanding of autoregressive model. Now this is a explicit density model. It is sometimes called as fully visible belief network or FVBN. What it is, that likelihood of image is being realized or modeled by the joint likelihood of each pixel in the image. So this is a basic understanding. So this is an image and this is the pixels. So joint likelihood and joint probability distribution of each pixel image. And now how it can be done? Now in this explicit density model, the chain rule is used to decompose the likelihood of an data into product of distribution. So what we have seen before, that we write in this format, that xi given x1, x2 to xy. That is probability of the ith pixel value given all the previous pixels. Now here also you can see in this image that this x1, x2, x3, x4, x5, x6 x7, x8, x9 and so on up to I minus 1 in this row measure order, all pixels are generated before xi, and so on. This in this way it is being generated. But anyway, in any direction, it can be in a zigzag way, in any other ways. So what is the basic goal? Have to maximize the likelihood of the training data. So in general, what we generally see that a neural network is used to realize this complex pixel distribution. Okay. So this is the basic understanding of this autoregressive model, and for example, fully visible Bayes network is a autoregressive model. So there are different kind of autoregressive models. For example, pixel RNN, pixel CNN, transformer, GPT, that means generative pre-trained transformer. So these are very famous models. So we see some of them. We start with pixel RNN. The pixel RNN is a deep learning model that used to generate the image pixel or images by pixel. So it is proposed by 2016 by Google DeepMind. Now, if this is an image, what we'll see that this image is first, this pixel is being generated, and then based on this pixel, other pixel, we'll see that this is the way. In this way will come. So this is the way this pixel RNN is used. So pixel RNN treats an image as a sequence of pixels. Now here you can see the order of sequence is in general very much user defined. Any pixel is row order, column order, or zigzag order, whatever. So pixel RNN treats an image as a sequence of pixels and predicts each pixel based on the pixel that comes before it. That we will going to see. So it generates a full image by generating a pixel at a time. Now see here this pixel, that pixel is generated, this pixel generated by this pixel, this also generated by this. So this pixel. Then when these two pixels are being generated, then from these and these, this pixel is generated, and this pixel is also generated, and this was generated. So you can see in this way the pixels are being generated. Now pixel by pixel, as we said, is being generated. So process is generally started in general from the left of corner, and in this fashion, in some fashion, it is being done. And RNN or LSTM is used to model the dependency on the previous pixel for the current pixel. So this RNN is basically used, or LSTM is used to this sequential modeling, because this is a sequential structure. So this sequential modeling is basically realized or implemented by RNN or LSTM. Okay. So generally two type of architecture have been seen. At first, row LSTM process the image row by row. This is a different way, but in row order. Each row depends on the previous rows plus previous pixel in the row. and another is diagonal BILSTM. Process the pixel along diagonals, something like this. Captures the larger context more efficiently. So architecture, we are not going in details architecture because there is a more advanced things there that will details. So then this pixel RNNs, what are the application? Definitely one is image generation, density estimation for images, image completion or inpainting. If there is some problem in image, there is some sort of repairment is required, something in painting can be done. Lossless image completion. So pixel 2, there is some drawback of this pixel. It's a very slow, because pixel by pixel. This is a very slow process and computationally also expensive. And if there is a very large images, it's hard to scale a very large image. So this is the major drawbacks of this. And in this way it is done. So you get the image. Okay. Our next model is Pixel CNN. It's basically very similar to the Pixel RNN, but they use the concept of masked convolution. Let's see. In Pixel CNN, uses the multiple convolution layers that preserves the spatial resolution, and in this case pooling is not used. So let's try to understand what actually being done here. Now here this is 3x3 patches, and there is a convolution kernel, and this convolution is done in this way. Now the major aspect that a mask are adopted in the convolution to avoid seeing the future context. What is basically important? Let assume this brown pixels we are basically predicting. Now in this convolution or in this patch, these pixels, this blue pixel has already been generated. So these pixels are visible to predict this. Others are not visible. So there is a mask is in here. This mask is being used, and it is, if it is multiply with it, that this only is being visible. The rest are not visible. Even this is also because this we are going to predict. The masks are adopted. So that concept is required. What is mask convolution? That is the important concept in Pixel CNN. It is a modified convolution operation used to ensure that when predicting a pixel, the model only uses the information from the previously generated pixel and not from the future pixel. That's what we exactly said the last slide. These pixels are already being generated, so only these pixels, what are the previously generated pixels, they are being used to predict this, not the future pixels. So in a standard convolution, the filter can access all neighboring pixels, which would violate the autoregressive property. Because if all the pixels, then this autoregressive property doesn't hold. That's why they use this mask convolution. So the Pixel CNN applies a mask, that is a kind of mask, to the convolution filter that sets a certain weight to 0, so that these are not being generated yet, it is going to generate in future. So that is going to make it 0. So it blocks the connection to the future pixels as a pixel to the right or below the pixel. And this procedure ensures that each pixel is predicted based on only on the pixel above and to the left. So you can understand this. So this mask convolution is one of the important concept for That is basically one advancement of the pixel RNN. What the advantage we are going to get? Since it is used CNN, training is faster than pixel RNN because we can parallelize convolutions, which has not been done in the case of pixel RNN. So, can parallelize the convolutions in the context region values known from the training. But still, for a 32 cross 32 image, need to a forward passes of the network 1024 times for a single image. So this is the pixels here. Now we are going to discuss some of the vision application, and in next few slides some of the NLP application which or where these generative AI models are being used. So first we see the vision task. In general, we have seen that the major task involved here is the synthetic image generation, since it is a generative AI models. So here there is a different type of downstream stack or specific computer vision task. First of all, this image to image generation. This image to image generation means it's given an image that there is a grayscale image is being given, and we have to colorize it, or we have to find out the corresponding color image or RGB image from this grayscale image. So this is called image to image generation. Another very interesting thing, that is called neural styles transfer. As we may have observed that there is a different images in different style. Some famous painters, they have a different way of drawing pictures. Sometimes called a very famous painter Van Gogh style, or this kind of. So it is possible that given a input image and given a style image, the input image can be transferred to this style given by the style image. A very interesting concept. You will see in this course. Another very interesting thing is called text to image generation. That given a text, can we generate the image? When we study the large language models, then we can see the prompt based generation. So this is some kind. But synthetic image generation, that means in medical image domain or some other vision application where this real images is very tough to get, or there is a certain data scarcity, the synthetic image is generated. Image in painting, that sometimes some image is corrupted or damaged. So in case this can be repaired, that's also been done because this is also some sort of generative image. So as a whole, we can see that there is a different vision task, and we have studied several models. Now if we try to understand how these models are being used for this kind of different task, we have idea that how this model, whatever we have studied, it's different model, We have studied autoregressive model this class. Before that we studied generative adversarial network. Then we studied the variational autoencoder. Then we studied diffusion models. So these models can be used for certain vision and NLP task. So let's see one example that where this kind of model used. So we just concentrate on neural styles transfer. So in neural styles transfer, that two images are involved. One image is the content image, that is the input image, and another image is called the style image. And you can see that this image is now transformed to this style image, and that essentially the essence of this style transfer. Now in this process, this is CNN based process, that two pretend CNN, there are two CNN are involved. One for image content features, so this generate this content image features. Another is style features. So this is a pretend CNN that is going to use or to generate the style features, and this is another CNN that is going to generate the image feature. And these two features somewhat concatenated or somewhat fed to another CNN that is somewhat generative image. So it generates some sort of, you can say, some sort of kind of generator structure, what we can use in GAN or some sort of decoded structures, and it generates this. So two types of loss is involved here. One is content loss, that means how whatever the image is being generated, how different this actual content. So one thing is very essential here, we are changing the style fine, but we try to keep the main content as the same. So people can understand this is a Mona Lisa image. If by the using of style transfer people cannot recognize the image, then the main essence will go. So that is very important to understand, that two features are somewhat merged to generate the image. So here we can say these features are combined to generate a synthetic or stylized image. It's supposed to have content like component, or this content like content image, input image, and the style like the style image. Both are input to this system. So this is the basic, very naive or basic block diagram of this neural style transfer, and that we can use this particular. Now we are going to discuss the generative model for NLP applications. In NLP application, generative models are being basically used for text generation. For example, the dialogue generation. As we all know now, ChatGPT is very famous, where there is a chatbots are being used to making conversations within or between a human chatbot or even between two chatbots. So there is a dialogue generation is there. Somebody is saying something, understanding that what is being said, and can answer it. Can we answer it? That is a very challenging task. And when we see or discuss these large language models, see this a lot of this kind of techniques are being used. for this kind of dialogue generation application. Another thing is called natural language processing, is language translation. That means, given in a particular language like English, can we change it to the Spanish? Or given in a German, can we change to the English? Or something like that. It is popularly known as machine translation or neural machine translation. Another very interesting thing is called image captioning. It is somewhat bit multimodal in nature, because here text and image are both involved. The previous two one are the text model it is used. Here image and text both modalities are used. What is the problem here? Problem is, given an image, can we say something about image, or can captions give some caption? That there is a image of sunrise. So can we write sun is rising and something like that. So this is also very interesting, because you can understand we have to find out the image feature. We have to form this image feature. We analyze this image feature. So what is the meaning of this? And according we create some context, and based on this context we generate some sentence or some words. So it's a very challenge. Next coming is text summarization. That you are given a paragraph, can we write 2-3 lines or make a summary of this paragraph, or given a big text, can we make a summary? That is also a very challenging issue. Another is VQA, that is called visual question answer. That given an image, it is also the bimodal or multimodal. The given image asks some question. That there is a cricket is being played with one image, and somebody says, what is the play, or what they are playing? You have to answer, oh yes, this is the cricket. This kind of application. So it's very challenging in nature. Let's try to understand some examples of how actually whatever we have discussed, different models can be used here. So first we start with language translation. In language translation, what we can see that a language translation model is a sequence to sequence model. That we have discussed few things before. This model consists of two recurrent networks, an encoder and a decoder. Okay. Maybe we can think of that these both are RNN or both are NST. Now, how they change from one sequence to another sequence? Just input sequence in English and the output sequence in Hindi. So sequence language translation means this. Now, there is a lot of challenges involved here, because we cannot say that the number of words in the first or input language or input sentence is exactly same the number of words in the output sentence, because both the languages are different. Two languages are different. So let's see how we proceed. So at each instant of time, or at each time instant, the word is converted to the vector representation by some word embedding like one-hot encoding or word-to-vec model. So this word embeddings. So what is your name? So it is what to vehicle. And these are being in a, this may be a kind of, you see, a very analogical kind of LSTM or RNN model. So these are the time instances. So encoder extracts the meaning of input sentence in context or the state. Okay. So what is important here, by analyzing these words, context, this encoder is a context and it is going to give to the decoder. So this decoder takes this context as input as this, and then each time step there is a two inputs here. One is this context or the hidden previous state, that next word in the input sequence for encoder, and the hidden state, the previous word from the output sequence of the decoder. You can say it is in Bengali. So whatever the particular word is already being generated, that is also coming as input to the next level. So Sapnar is basically used to now, and Apnar Nam is basically used, and so decoder will generate the translated text. So this is a very interesting kind of model. Why it is important at this particular position of this course, that this architecture is to somewhat familiar with us, because we have discussed RNN based modeling or context modeling through RNN. In our next course of study, we'll go for transformer, and then we try to understand what is the attention and what is the self attention, and how these attentions are basically make this transformer architecture more useful or more improved over these structures. Now we are going to discuss another multimodal vision and language application by this generative model. This application is called visual question answering, popularly known as VQA. In this application, the main task is to predict some answer to a given question associated with a given image. Now we can see this figure. Now a boy is flying a kite. This is the input image. So given this image, the question is, what is he flying? And the intended answer is kite. So what is the job of this application or this task is that, given that image with the associated question, going to give the correct answer. And you can see here there is a different things: kite, bird, balloon, drone, and kite is the most probable answer, and in this case it is close to 1. The probability is close to 1. Now the question is how we design this particular model. Now here, first of all, that there is a two basic modalities. One is the image, this is input image, and there is a text. So two input modalities. So first of all, we have to understand how this text modality is being embedded or encoded to the model. So here what it has been used, that a dense word embedding, for example what to make, that has been used for pre-process the question. So this sentence is first being converted to a vector word by word using the word method. Then it is fed to this RNN. Okay, so this RNN is what the job of this RNN, that this RNN is going to analyze this sentence and try to find out the context, or in a very simplistic understanding, the meaning of the sentence. And this contextual understanding is represented here at question of the feature vectors. So you can say this kind of a context vector or something like this, or you can say the feature vector here. On the other hand, the input image it is given here, that is fed to a convolution neural network. It is a pre-trained convolution neural network, and that is used for the image encoding, and they will generate the image feature. So it is basically a CNN feature. Now these two features, this is the textual feature, the questions, and this is the image feature. These are to fed to another neural net. Okay, that may be a CNN or similar like, and that is going to give the answer of the question. Okay, so the combined image and questions features are fed to a neural net for predicting the answer. This setup is used for the VQA. This is a very simple kind of setup, but if it is trained properly, then they are going to give this answer. This is a very simplistic model. The output may be given a probability score. This is the probability score. Okay, so this application is called visual questions. So what is important to understand here, that how the multimodal data are being analyzed for a given application, and that is a very important understanding of this generative application. Because why it is sometimes it may be confusing that it is a only one, this is maybe a discriminative, or it's a classification. No, it may be the possible. The answer is not always a single word, it may be a multiple word. Even we don't know what will be the answer, what is the modalities. Textual modality is okay, but how many words, that we don't know at prior. In that sense, it is a kind of somewhat generating. So this is the basic understanding of visual question answering. This is a very primitive or naive concept. It is just a kind of definition. Now, that is possible that there is a lot of different, there is a very rich literature associated with VQA. So interested person can go to this literature, and still this VQA is being researched and open research topic. Okay. Our next application is image captioning. Now it is again a multimodal function. There is an image feature and a text feature. Now what is the problem of image captioning? In image captioning, this is a task in AI that automatically generates a descriptive sentence for a given image. So it's more specific for a generative modeling. Given an image, can we say something about this image? That is called image captioning. Previously, that a question is being asked. Our task was to answer the question. But here no question is given. Rather, it is only an image is given. But we have to describe. So it is a cross modality kind of job. Given input in a particular modality, in this case is image, and we are generate a text that in another modality. So you can say it's a image to text model. Okay, so as we just said, it combines techniques from computer vision and NLP to understand the visual content and express it in a natural language. That is called image captioning. Now, how we can do this? Typically, a CNN is used to extract important visual feature from the image. First, we can extract the visual feature. While a language model may be a transformer or RNN or LSTM is going to generate the caption word by word based of these features. Now, transformer will have not been covered yet. That we're going to see next. And this recurrent neural network, this RNN or LSTM, that we have already discussed. So why we discussing this particular problem, although in a very nutshell, but still, that we want to think how these kind of problems can be solved using whatever model, generative model we have learned, and what is other model which we're going to be discussed next. Okay, now let's try to understand the very basic architecture of this. Here the same image we have used, that this extract spatial feature from the pre-trained CNN. So this is the CNN and this is the image feature. Now from this image feature, we try to extract the attention. Now we know what is attention because we have discussed this in the context of RNN in some previous discussion. So from feature vector, we find the alignment score, that also been discussed, and then we determine the attention. Okay, so attention is basically this, that given a feature vector, which part of the feature vector is more important, rather going the same priority to in this input modality. So let's try to understand from this image. Now given this image, this boy is a very region of interest. This kite is another region of interest. Another thing that is bit semantically important, that this flying thing, that this boy is flying a kite. So these are very important description or important attributes of this image. That should be what we should be more priority to this rather than the sky and this lands and this some greeneries, like that. So that is the basic idea of attention. Attention is basically try to find out the patches or some the in that granularity. It may be object, it may be something else. That what we are going to do, that these modalities or this part of the image should be given more priority rather than the entire image. So this is a very important aspect of. Now this is the some kind of encoder kind of part. Now this is a kind of decoder. Now encoder means that given an input we try to understand. Now this attention is given to this decoder, and that is basically our very familiar structures, kind of RNN structure or LSTM structure. Now here you can say this X1 is somewhat generated. Now X2 is important. Here you can say that we basically producing a sentence. A boy flying a kite or something like that. So in first time instance, it is word by word generation. So first time instant, it is boy. The input is basically 0 is also, we can say, coming from this attention. And then this boy, what is being generated by first time instant is being as input to the next time instant or next node of this recurrent neural network. And this H1 is coming. This is also active. So boy is input here, and then flying is coming, and so on. So this is the basic understanding of this decoder model. So one is very interesting thing to understand. Previously the similar architecture we have understand or we have discussed about that sentence to sentence machine translation, or more specifically neural machine translation. But here we can understand that this kind of architecture can be easily extended to the multimodal translation, to image to text. In some other time we'll see that text to image, that is some prompt based image generation, we'll see for more advanced when we see LLM or some that kind of vision transformation or vision language model that we can understand. So that is the basic essence of image capture. And here, that what I just said in the previous slide, why this particular problem we are discussing at this moment. But basic intention that we want to explore attention, because what thing we understand that in this kind of application, what is the main thing is that attention. And rather than this kind of CNN based attention, can we use some more sophisticated structure? And in this time of research, the transformer is proposed. So this kind of problem is create a kind of a situation so that this transformers architecture, which is basically depends or basically developed of different kind of attention modeling, like self-attention, multi-attention, and so on, so that we are to understand. And transformer is at this moment or in this deep learning era being playing a very vital role. Okay, so the next lecture will start transformers. So in this lecture, what we have discussed, we introduced autoregressive model. Then we two models we have discussed. One is pixel RNN and pixel CNN, and then discuss generative AI for vision. Some examples discussed. In our next lecture, we start transformers. Thank you very much.